ASTRA from the Space Hardware Club at the University of Alabama in Huntsville is proud to present our 2026 System Acceptance Review. This year, the team consists of over 50 dedicated members who have worked tirelessly throughout the development cycle to redesign our science module and communication system, as well as optimize our core rover platform and our robotic arm.
This year's electrical subsystem focuses on optimization and refinement, utilizing the same field-tested 4S LiPo battery and main CAN communication network. Dual ESP32 microcontrollers on core and ARM have been replaced with singular, upgraded ones capable of servicing both the main CAN network and their submodule-specific motor CAN networks. Additionally, an automatic low-voltage battery cutoff is being implemented to prevent over-discharging our batteries.
Our main general software improvement this year was to migrate our entire build system away from Ubuntu and towards Nix for reproducible and declarative deployments. When paired with the NixOS operating system, it gives us the ability to reliably test on any device and then instantly operate directly on the rover. With NixOS, we can sustain the complete destruction of our main rover computer and be back up and running in under an hour due to our software-defined system configuration. This competition cycle, our core rover software underwent iterative improvements. We upgraded our ROS2 topics to improve interoperability with the autonomous control library NAV2. We also tuned our quality of service profiles for more reliable communication between the rover and the base station. Finally, we're working to reduce technical debt by cleaning up outdated code.
This year, the core rover submodule underwent numerous changes. The objective of our revisions this year were to reduce mass, and this was accomplished by redesigning the wheels and suspension members, as well as adding a new cooling system. We manufactured all these components in-house using a wet layup, prepreg, and filament winding process.
During this competition cycle, the ARM's main focus was on optimizations from last year's design, with an emphasis on weight savings and improved inverse kinematics. The bearing stack turret assembly's main central gear, as well as two other central gears, have been machined down to accommodate weight savings. This year, for inverse kinematics, we were complementing our ROS2 stacks with ROS2 Control and MoveIt2, which is a motion planning library and inverse kinematic solver. Using inverse kinematics to control the arm, instead of manual per joint inputs, it allows for quicker, more intuitive movements and actions, which leads to better control for the operators.
The base station submodule has undergone a complete overhaul this cycle. A Valve Steam Deck has replaced one of the two previously used Latte Panda 3 Delta single-board computers. The displaced Latte Panda has been moved into a newly redesigned tracking antenna, where it controls a belt-driven motor which accurately tracks the rover across the operational area. The improved computational power of the Steam Deck has aided the transition of base station's control software, moving away from the previously web-based user interface to a system developed with the Godot game engine has provided for more complex graphical systems and greater integration with the rover systems, such as visualizing the IK system. Custom forks of the ROS-Bridge and ROS-Sharp packages have marked a 10 times reduction in startup time when compared to the previously Docker-based system.
The autonomous navigation module has undergone major upgrades since last year. The object detection system has moved to a YOLO v26 model trained on a custom dataset that can reliably detect mallets, water bottles, and rock pick hammers. The rover determines its global position using GNSS satellite data fused with WinCoder, IMU, and VIO measurements through an extended Kalman filter. It processes point cloud data from a front-mounted Z2I depth camera to navigate to specific coordinates and then conduct a sweep search pattern to locate competition objects within the surrounding area.
We have completely overhauled the science configuration this year to enhance reliability and precision in soil collection and chemical distribution. Key upgrades include a new linear actuator system for surface and subsurface sampling, a centralized fan system, and servo-driven mechanisms for distribution of chemicals and soil sorting. Integrated with the rover's comprehensive camera suite, these systems enable detailed stratigraphic analysis and site documentation to satisfy all mission requirements.
Chemical tests are conducted on collected surface samples. Returning tests consist of a bisinkinetic acid assay, a methylene blue test, and an acetic acid test detecting proteins, perchlorates, and carbonates respectively. A new chemical test for the cycle is the glucose oxidase test, which detects glucose. Once a viable site has been selected, the subsurface sample is collected with a newly designed drill, which seals in situ once a depth of 10 centimeters is reached, preventing contamination. A temperature and humidity probe is built into the drill to read conditions at depth. Items in development for deployment at URC include a custom laser-induced breakdown spectrometer to determine elemental composition of the site.
ASTRA's drone module is fielding many upgrades this year, including new motors, carbon fiber frames and legs, a custom battery pack, and control over a pan-tilt-zoom camera gimbal for enhanced observation capabilities.
This concludes our System Acceptance Review. Thank you for the consideration. We look forward to seeing you in Utah this summer.